Hello there, and welcome to this course as part of the summer school in quantum field theory. I say summer school, I guess we're not quite in the summer, but thank you for joining anyway. So let me start by introducing you to who I am. So my name is Chris McCabe. I'm a lecturer in theoretical physics at King's College London. My research is mainly in the area of the phenomenology of dark matter, so thinking about how we can detect it and how we can test it and so on. So at the minute I might be working with some of the people watching this video. So I work with some experimentalists trying to find dark matter and work in some theoretical stuff as well. So let's discuss how I think and hope these lectures are going to work. So obviously I'm recording these as video lectures, and I taught a course online at King's last semester, and the way that King's taught us and emphasized that we should teach online is to break our normal lectures into smaller chunks, so into chunks of anywhere between 5 and 15 minutes. It's kind of seen to be the ideal. So I'm going to try and replicate that here to some extent, and then I'm going to record this in little chunks, and then there'll be sort of transitions, which will just be when the screen fades to black and then fades back in again. So if you do want to take a very short break during the videos, during the 50-minute longer videos, and that would be the ideal time for you to do that. So there is still a constraint that these videos have to fit into a normal lecture slot, so they will all be strung together to make up the larger lecture. Okay, the other thing I should talk about is the style of the lecture. So I'm going to do handwritten lectures as we go, so sort of replicating what you might have in a Blackboard lecture. I think for this subject, having this handwritten style is particularly beneficial because as we'll see, there's quite a bit of algebra involved, especially when we get into some of the commutation relations and so on later on. And hopefully, as I go through them, it will give you the confidence as well to go through these calculations as well. So when you come away from the school, and if you want to learn more about field theory and go further than what I cover, you'll have the confidence to do that because you'll have worked through the calculations. Okay, the other thing I should mention is some of the other material that you'll have to supplement the course. So obviously I'm going to be recording these lectures, but there's other material as well that comes with the school. So you should have access to some pre-school lecture notes and lecture material. And so I'm going to briefly recover some of that material again. So this is one of the disadvantages of video lectures, is that I don't get to see you in the room. So if I'm in the room with people, I have a much better gauge of how much people have understood from those preschool lectures and how quickly I can go through it. At the minute, when I don't have you in front of me, I'm having to guess how much I should do a recap of that preschool material, but hopefully I'll get the balance right. I'll try my best, but I'm going to go through some of that preschool stuff again, especially in the first couple of lectures. You also have typed lecture notes for the course itself, so that will cover the material that I'm going to go through. I should admit or tell you about the fact that written material was basically written by other people, so I've made very small tweaks to it. So it won't follow, it won't just be a typed version of what I'm going to tell you in these lectures. It'll be slightly different, and that's on purpose on my part. So when I learn the subject, or when I learn any subject, I like to have multiple sources at the same time, because multiple sources tend to emphasize slightly different things. So my video lectures will tell you one version of the story. Those lecture notes will hopefully tell you the same story, but emphasizing different parts. And then, of course, you're going to have the problem sets where you can discuss the problems during the tutorials with your tutors. And your tutors may emphasize other aspects of the course, things that they find challenging or interesting, or things that they can supplement these videos with. And then, of course, the other thing is that there's many textbooks on field theory, quantum field theory. So this is the one I've used. This is the one I learned the subject from. So this is Peschken and Schroeder. My lectures will probably kind of subconsciously follow a style similar to Peschken and Schroeder, because that's how I learned the subject. But there's many other good books on field theory by Z, by Schrodnicki, by Schwartz, many others as well that I could mention. So there's many, nowadays there are many excellent textbooks on field theory. Okay, so that's the end of this little chunk. So as I promised, I'm going to break these videos into small chunks. So the screen's going to fade to black, and then it will immediately fade back in for you. Like I say, if you want to take breaks, this would be a good chance for you to take those breaks. So let's begin the course properly by thinking about what quantum field theory actually is. Maybe you have your own ideas. Maybe it's worth pausing the video and reflecting and thinking about what you think quantum field theory is. I suspect there are many acceptable answers. So if you did pause the video and if you did think about something, there's, I say, many options. I mean, let me give you some things that I've seen around the place. So one textbook I read described quantum field theory as, or it is the union of quantum field theory, of quantum mechanics, so QM, quantum mechanics, and classical field theory. So that's kind of a very simple definition. Quantum field theory is just the quantum version of classical field theory. Okay, so the reason I've given you this very simple definition is because to understand quantum field theory, we need to know something about classical field theory. So I'm going to start this lecture series by reviewing some of the concepts from classical field theory, because if you're not confident with those concepts that come up in classical field theory, then quantum field theory is really going to be a challenge. So we're going to start by reviewing those concepts. And there's another couple of answers I can give you for what quantum field theory is. So there's a nice review article by Frank Wilczek. Frank Wilczek is a very well-known, this is the archive number, I should say, where I'm getting these definitions from. So Frank Wilczek is a very well-known theoretical physicist. He won the Nobel Prize for his work on discovering asymptotic freedom. He's, he has the type of PhD supervisor that you want to have. He did his Nobel Prize winning work during his PhD. So his supervisor, Gross, gave him this nice problem that they worked on together. And that's what they won the Nobel Prize for. So hopefully your PhD supervisor will also give you work where you can win a Nobel Prize. Of course, Wilczek has done many other things beyond that, so he's very much deserving of all of the honors and glory that has been bestowed on him. But let me tell you about what Wilczek, this smart guy, thinks about what quantum field theory is. Okay, so he has this sort of fairly technical definition that I want to give you because it has some concepts that will pull out as we go through the course. So he says quantum field theories are theories where the basic dynamical variables, so the things that are going to be in the theory, the basic dynamical variables are, and now here's some technical language, they're operator functions of space and time, or of space-time. Okay, so these operator functions of space-time are what we think of, or what are quantum fields. Okay, so quantum field theory, okay, the key word here is operator functions. Okay, and the key point about these operator functions, the thing that really makes them quantum instead of classical, is that as with ordinary quantum mechanics, where we have commutation relations, these operator functions are also going to obey commutation relations. So commutation relations are a key part of quantum theories in general. That was one thing that Wilczek used, used to define what a quantum field theory is. There was another very important point that he emphasizes, and that's that in these quantum field theories, the interactions, so interactions are important because otherwise you just have particles moving around that are very boring because they just never interact with anything. Okay, so the interactions of these fields in the theory, these are all governed by very basic principles, basic underlying principles, okay, which are very important. So for instance, principles of locality. Our theories are local, and the other important principles are various symmetries. So things like respecting the Lorentz symmetry, so making sure they're consistent with special relativity, respecting gauge symmetry, so having these internal symmetries that the theories are governed by. Okay, so we're not going to get into the details in this course of those symmetries, but hopefully in some of the other courses, in the standard model course and so on, you will see the importance of those basic principles in action. So that's what QFT is. Okay, so as I said, this is a nice archive article by Wilczek where you can get into some of the details, but the key points are we're going to have operator functions. These are going to be our quantum fields. So that's what quantum field theory is. You could also ask, why quantum field theory? Why bother studying this subject? We're going to see it's a bit, at least the formalism we're going to look at can be a little bit tedious, to be honest. Okay, well, all these commutation relations that we're going to see, a bit of a faff doing some of the calculations. So why do we want to bother going through this? Well, the reason why we want to look at QFT, okay, well, there's one very nice point that Wilczek emphasizes, and that is that QFT explains why particles of the same type are indistinguishable. That is to say, it explains why if I have one electron in this room, so I'm recording in London, and you have, so say I have an electron in London and you have an electron in some other part of the country or other part of the world, we know that they're indistinguishable. Now, quantum field theory explains why those two electrons are indistinguishable, and that's because it's not the electron particle which is the primary object. Okay, primary object is the field. It's the fact that I have this electron field which is spread throughout the whole universe, so it's the same field which is in London and which is in your location. This electron field is the primary object, the most important object. Okay, and the thing that we think of as the particles, so the electrons, these are just excitations of the more basic thing. Excitations. We have one field throughout the whole universe, and then we just have different excitations, but we have one field underlying it. That's one nice thing about quantum field theory. We can understand this feature. And the other thing which is very important is that it incorporates antiparticles. Okay, so we know that the world has antiparticles in it. Quantum field theory very naturally has to have antiparticles, and it is a formalism which in general allows for the change in particle number. Okay, so it incorporates antiparticles and changes in particle number. Okay, because the normal non-relativistic quantum mechanics that you learn as an undergraduate, where you have a particle described by a wave function, so for instance the electron in the hydrogen atom described by a wave function, in that formalism of quantum mechanics there's no way to change the particle numbers. There's no process in the Schrödinger equation which allows that electron to change into anything else. But quantum field theory is a formalism that allows this to happen. So, it allows, the Higgs to go to gamma gamma or any other reaction that you want to deal with. So this naturally incorporates all of these things. Okay, so there's a couple of reasons for why we want to do this course. As I said, there might be many other things that you can think of. These are some that Wilczek particularly picked up. Having discussed what QFT is and why you might want to study QFT, let me very briefly sketch for you what the outline of this course is going to be. So basically it consists of four points. So we're going to start by recapping classical physics. Okay, so there's a lot of concepts from classical physics that we're going to have to bring over to quantum field theory. And this is one of the challenges of quantum field theory, I think, is that it's a course which has a lot of concepts coming from different parts of physics, and there's also some it can be technically demanding as well, okay? So I want to ensure that you are familiar with those concepts from classical physics, because if not, it'll make the course much more difficult. And in particular, the classical thing we're going to look at is the classical theory of the real scalar field. We're going to look at the classical field theory of the real scalar field. Then we'll start to look at how you quantize this theory. So we're going to first think about the free theory, so the free real scalar field. We'll see how we can quantize that. But theories that have free particles that don't interact in any way are a little bit boring. Then we'll think about how we add interactions, again in the context of this simple free scalar field theory. And then we'll look at things like matrix elements and Feynman diagrams, and how you can start to relate, how you can start to derive things like Feynman rules, and how that allows you to calculate things like cross sections and so on, which are obviously relevant for particle physics. Okay, so that's the kind of the rough outline of the course that we're going to be going through. Okay, so we've discussed the course, so who I am and how the course is going to work. We've discussed why you might want to do quantum field theory, why it's a subject worth learning. Before we get into the real meat of the subject, I just want to briefly discuss what I'm going to assume that you already know. So I'm going to assume that you are familiar with two things. First, I want to assume that you're familiar with four vectors. Okay, so let me tell you about the notation I'm going to use for four vectors. So for space-time points, we're going to write x mu. Mu takes the values 0, 1, 2, and 3. Okay, so this is shorthand for these three coordinates. So there's like four values. So we have one time coordinate and we have three space coordinates. And we have up and down vectors, or covariant and contravariant vectors. So my up index has a plus sign in front of the x, in front of the space coordinates, and my down index has a minus sign in front of the x coordinates. So in other words, I'm using the convention, so-called mostly minus convention, where my metric has a +1 and then 3 -1. So this is kind of the normal, or the most commonly used convention in particle physics. There are, of course, some books which will put a -1 in the time placeholder and a +1 in the space parts. And I'm going to follow this mostly minus convention. And the other thing I should define are the derivatives. So my derivatives in this convention then are, well, I've got a spatial derivative, so I'm going to use it. dt is short for ddt. And then we have the spatial derivative, this nabla symbol, and then the up indexed version. As always, I just swap the sign in front of the spatial bits. This is the convention I'm going to be using. The other thing I will do, so whenever we look at when we look at the product of four vectors, so for instance, k mu, x mu, okay, so this of course is simply a shorthand way, oops, not a dot x, which is shorthand for this. So I'm using the metric tensor here. And if you split it into the component parts, we have, well, let's define what k is. So this wave vector typically has the time component is omega, and the spatial bit is the free vector k, so the wave vector and the frequency. Okay, so this product then of k dot x is omega t minus the 3 vector dot product k dot x. Okay, so sometimes I'm going to write k dot x. So if there's a line under the k dot x, that means it's the 3-vector quantity. So this is the dot product of 3 vectors. And if it's k dot x without the lines underneath, this is the 4-vector dot product. So this is shorthand for k mu x mu. But sometimes when we get onto exponents and things, it's simpler to write k dot x instead of having these Greek symbols floating around. So the other thing that's one thing I'm going to assume you know. So the second thing is kind of, I guess, already being used in these equations here. So I'm going to assume that you're familiar with this natural unit system, what I've already been using. I'm going to assume you're familiar with natural units, and throughout the course we're going to use the convention where we said h bar and c equal to 1. As I said, we've already set c equal to 1 in these definitions of our 4 vectors. Okay, so those are the 2 things that I assume you already know. Next, we want to move on and give a brief recap of important results from classical mechanics. Okay? So you might ask, why are we doing classical mechanics in a course in quantum field theory? Well, one of these definitions we gave of quantum field theory is it's the union of quantum mechanics and classical field theory. So we need to make sure that we review and understand the concepts from classical field theory. So I'm going to first give a recap of classical mechanics and then move on to some of the classical field theory. So there's 2 main things we want to talk about from classical mechanics. So the first is Lagrangian mechanics, and the second will be Hamiltonian mechanics. So start with the first. So we're going to first of all introduce an important quantity, so-called Lagrangian. Okay, so this is given the symbol capital L, and this is a function of coordinates, which we normally write as q, and these coordinates can be a function of time. There's the coordinates, and there's the time derivative of the coordinates as well. So this symbol q is normally used because these are generalized coordinates. So they could be the familiar x, y, and z Cartesian coordinates, or they could be coordinates in a different coordinate system, like spherical coordinates. So it could be r, theta, phi, or something else. Okay, so one of the nice advantages of Lagrangian mechanics is that we can work with these generalized coordinates very easily. And then q dot is simply the time derivative of q. So for many, many systems, we can work out what this Lagrangian function is. Okay, so for many systems, this Lagrangian simply takes the form of the kinetic energy in the system, T, minus the potential energy. Okay, so this is the kinetic energy, and V is simply the potential energy. Okay, so that's true for many, many systems. It's not true for all systems. So there's a well-known example where the Lagrangian is not of this form. Okay, so for instance, a particle in a magnetic field isn't in this form. So for a particle in a magnetic field, it does go like the kinetic energy, but then it doesn't quite go as minus V. It takes a different form. Okay, so it ends up depending on the vector and the scalar potential in a different way. Okay, so we're not going to particularly use it in this course. I just thought I'd mention it. So for all of the examples that we work with, it's going to take the form of T minus V, but just to emphasize that it doesn't have to be that form. There are examples that are known where it's not. Okay, but as I said, for the simple, or for the theories that we're going to look at, it takes this form. So let's look at one particularly simple example that we're going to return to multiple times in this course. So this is a simple harmonic oscillator. Okay, and let's work on some of the properties that follow in this simple theory. Okay, so of course, the simple harmonic oscillator a theory that describes, for instance, a mass on a spring. So here's a spring, got some mass m at the bottom. Okay, and that's introduce a coordinate system. So typically you introduce a coordinate, that's called an x, which tells you about the displacement of this mass away from its equilibrium position. So in this case, we can write down what the kinetic and the potential energies. So the kinetic energy T is simply a half mx dot squared. And the potential energy of this system is simply a half k x squared. And therefore, the Lagrangian for this from this system is just T minus V. Okay, great, you might say. We've written down the Lagrangian, which is T minus V. So what do we do with it? Well, the nice thing about the Lagrangian is that once we have it for the system, we can work out what the equations of motion are for that particular system. Okay, so the equations of motion, yes, I can, I'll simply write, oops, not M, I'll write EOM for equations of motion. Okay, the equations of motion follow from this Lagrangian, so they follow in particular from an important principle called the principle of least action. We are going to use this principle of least action to work out what the equations of motion are, because then we can understand dynamics in the system. So principle of least action, well, we'd better define what the action is. Okay, so the action is normally given the symbol S, and this is defined in terms of the Lagrangian. So it's the time integral of our Lagrangian function. I guess we can put on limits from T1 to T2. Okay, so in the pre-lecture notes, I'm not going to go through the details here, but in the pre-lecture notes, you can go through you can see in detail how this principle of least action leads to a very important set of equations. So the principle of least action, oops, you will see can be written mathematically as the constraint that the action is stationary. So the first derivative of it is 0. So we call it the principle of least action. I guess a better thing might be that it's a stationary action, because it's not necessarily the case that the action is minimized. We just know it's stationary, but we call it the principle of least action. But this principle, once you force that delta S is 0, you can show and you can derive that this occurs, delta S is 0, when my Lagrangian satisfies the following equation. So the equation is the partial derivative of L with respect to Q must equal the total time derivative. So note here, these are partial derivatives, and this is a total derivative. The total time derivative of this quantity. So again, we're now using partial derivatives of L with respect to the time derivative of the coordinate. So if this equation holds, so if this equation holds, which involves the Lagrangian, the action is going to be minimized, or at least stationary. Okay, so this equation, very important. This is called the Euler-Lagrange equation. So the Euler-Lagrange equation, coupled with a form for L for the Lagrangian, allows us to work out the equations of motion. Okay, so let's look at our example for the simple harmonic oscillator. We're down above. Let me remind you what the Lagrangian was. So we used that our generalized coordinates were x above. So Q is x and Q dot is x dot. Yeah, so here we labeled x as the displacement away from the equilibrium position. And we used that L was a half mx dot squared minus a half ax squared. So we just need to work out what dl dx is. So that's the left-hand side of my Euler-Lagrange equation when I set q equal to x. So dl dx is simply minus kx. And then I need to work out the right-hand side. So we need to do dl x dot. Simply going to be mx dot. Okay. My Euler-Lagrange equations then become d dt mx dot is minus kx. Or in other words, we get that the equation of motion, since m is the mass, which doesn't change with respect to time, so the time derivative only hits x dot. So we get that x double dot is minus k over mx. So this is also, of course, the formula that you would get from Newtonian mechanics. So we have the acceleration is minus k over m times x. So you might ask, why bother with this formalism if I can also get, in the end, this equation of motion, I can find it from Newtonian mechanics relatively straightforwardly. So why introduce all of this stuff? Why introduce the Lagrange and the Euler-Lagrange equations and so on? Well, there's a number of advantages of the Lagrangian approach. Okay, so let me give some of them to you. So one nice thing is that they hold, or that the formalism holds in any coordinate system. So that's part of the reason why we use this Q notation. Emphasize that. So particularly holds in non-inertial frames as well as inertial frames. So that's going to be a useful property. If any of you have actually taken a full course in classical mechanics, you'll know that this formalism often makes complicated problems very easy to solve. I remember when I first took a course on this as an undergraduate, I was given all of these complicated problems with spinning tops and rings spinning within rings and all of this multiple pendulums and all sorts of complicated things, which would have been, I wouldn't even know how to go about approaching solving them in Newtonian mechanics. But in this Lagrangian formalism, it's relatively straightforward. You just have to work out what the kinetic energy was in terms of the coordinates that you would introduce. And then, like magic, you put it through the Euler-Lagrange equations and out pop the equations of motion. Okay, so I thought this was magic the first time I learned this subject because of the problems that you could now solve that would have been very tricky in Newtonian mechanics. And then the third reason that this turns out to be a very powerful technique, okay, and we'll see that partly in this course. So this Lagrangian formalism is going to be generalized to much more complicated problems. We can generalize and we can tackle much more complicated systems with this Lagrangian approach, which we couldn't do with Newtonian mechanics. So it's not possible to generalize Newtonian mechanics in the same way. Okay, so that's a very lightning quick introduction to Lagrangian mechanics. So I said I was going to introduce two concepts from classical mechanics. So we've done Lagrangian mechanics. Second one I want to talk about is Hamiltonian mechanics. So Hamilton was a famous Irish mathematician slash physicist who introduced this very important formalism that I'm sure all of you have met the Hamiltonian in quantum physics, and hopefully most of you will have met it in classical physics as well. So let's quickly go through what happens in classical physics with the Hamiltonian. So with this simple harmonic oscillator example that we just looked at, you may have noticed one thing. So we saw that when we took the partial derivative of the Lagrangian with respect to x dot, we find that this was mx dot. And you will hopefully notice that mx dot is just the mass times the speed. In other words, it's the linear momentum of this system. So we can sort of generalize this very slightly and define what's known as the conjugate momentum. So the conjugate momentum is given the symbol P for momentum, okay? And it's defined to be the partial derivative of L with respect to my generalized, with respect to the time derivative of my generalized coordinate Q dot. So in this simple harmonic oscillator example, it gives the linear momentum. In problems with rotation, this conjugate momentum can give you the angular momentum instead. So we use the symbol P, but it doesn't mean it's just going to be the linear momentum. It can be, as I say, in rotational problems, it could end up giving you the angular momentum, but it gives you something which is a momentum. Now, what happens in Hamiltonian mechanics is Hamiltonian, yeah, spelled correctly. So Hamiltonian mechanics does something very important. So Hamiltonian mechanics replaces the time derivative of my coordinate Q and replaces it everywhere with P. Okay, so Q dot rather does not enter into Hamiltonian mechanics. Instead, we have P. And in Hamiltonian mechanics, Q and P are put on an equal footing. Okay, so in Lagrangian mechanics, Q dot, well, it's just the time derivative of Q. We see how it's related to Q. You just take the derivative. In Hamiltonian mechanics, we really think of Q and P as things that are put on an equal footing with each other. So we can define an important quantity, which is the Hamiltonian. The Hamiltonian can always be constructed in the following way. So as I said, it's a function of Q and P, and we'll also put in the time. So in general, Q and P can both depend on time in some way, so let's put in the time dependence. And we can always construct the Hamiltonian, this H, with the following operation. So we take the product of P times Q dot, and we subtract off the Lagrangian. So the Lagrangian, remember, is a function of Q dot, and Q dot can depend on T, so let's put in the time as well. So this is simply an example of the Legendre transformation. This is a Legendre transformation that allows me to go from a function with Q and Q dot to a function that depends on Q and P. Okay. So next I want to manipulate this Hamiltonian, this H function, and show how you can derive an important set of equations called called Hamilton's equations. And Hamilton's equations are what are going to allow us to work out the equations of motion in this formalism. Okay, so let me show you how we can derive Hamilton's equations. So we start by considering dH, so the differential element of H. So dH is simply going to be, well, we can use our definition here. Okay, so it's going to be P dq dot plus Q dot dP. So just using the chain rule or the product rule, whatever the rule is for differentiation. Product rule, I think. Should know these terms. And we subtract off delta L. So dL we can write as dL dq plus dL dq dot q dot plus, since we'll put in the time derivatives, we'll do dL dt as well. Okay, now with our definition of what P is above, so we can use that P is dL dq dot, that's our definition. We can substitute in for P in the first term. Okay, and the reason we want to do that will become apparent in just a second. Let's write down all of the other terms. Okay, the reason for making that substitution was that you see that we have the same terms and they enter with a minus sign. So they cancel out exactly. Okay, so we're just left then with three terms. So dH is q dot dp, so something that depends on dp, something that depends on dq, and something that depends on dt. Okay, so that's one formula we can find for dH. So we've used our definition, this Legendre transformation, to find that dH must take this form. But we can also just write down what dH should be, knowing that it's a function of p and of q and dt. Okay, in other words, we know that dH, so it depends on p, it depends on q, and depends on fix that. So it's dq dq, yeah, it's dH dt. Okay, so that just follows from, as I said, from knowing that the Hamiltonian is a function of p, q, and t. So we can start to identify terms here. Okay, so we can do this by matching the different terms that have the same, for instance, dt bits, the same dq bits, and the same dp bits. So let's match the dt bits first. So we find that dH dt is just minus time, the partial derivative with respect to time of the Lagrangian. We can read off an equation which we do for q dot. Okay, we can find how q dot is related, and we can do that by just setting that these two terms must be equal to each other, so they both are simply the dp parts. Okay, so we must have then that q dot is dh dp by dp. In other words, when we take the partial derivative of the Hamiltonian with respect to p, it tells us about how this coordinate now depends on time. And then we must have that these two terms are also equal to each other. So we must have that minus dl dq is dh by dq. Okay, so this third one, so these two already look like quite nice equations. This third one isn't so intuitive at the minute, so we have to tweak it a little bit. So we can tweak it a little bit using the following. So we know from the Euler-Lagrange equation that the total time derivative of dl dq dot is simply dl dq. Okay, and we know that the definition of p is that p is dl q dot. So in other words, we put these two together, we see that it's p enters in here. So we have dl dq is, we write it as p dot. So it's the total derivative with respect to time of p. Okay, and from the equation we have above, we see that dl dq must equal minus dh with respect to q. Okay, so this is the third equation that we have then. We have that the time derivative of p is simply the partial derivative of the Hamiltonian with respect to the coordinate q. Okay, so these three starred equations that we have, this one in a box, the three starred equations that we have, so 1, 2, and 3, these are what are known as Hamilton's equations. And it's Hamilton's equations, Hamilton's equations that allow us to find the equations of motion. Okay, so let's quickly run through an example of how this all works in practice. So again, we'll use the simple harmonic oscillator example. Okay, so we've already found what the Lagrangian is for this system. me remind you, it's a half mx dot squared minus a half kx squared. So we can find out what the momentum variable is, what the conjugate momentum is. So it's going to be dl by dx dot. In this case, it's simply mx dot mass times the time derivative of x. And once we know L and once we know P, we can work out what the Hamiltonian is. So as I said, we can use this definition that it's x dot times P minus L. Okay. Let's substitute in for P. So we get mx dot squared for my first term. Substituting in for P, and we should subtract off the terms in the Lagrangian. Okay. So when we simplify this, we get a half mx dot squared plus a half kx squared. So we're not done. Okay, although we've got it in a nice form, we're not done because the Hamiltonian is a function of P and of the coordinate, which in this case is x. So we have to finish by ensuring that we have this as a function of P. So this is trivial to do in this instance because we know P is simply mx dot. So in other words, we can get rid of the x dot. We can just substitute in for P over m where we have an x dot. And when we do that, we find that the Hamiltonian is P squared over 2m plus a half kx squared. So now we have this Hamiltonian function, which is a function of P and which is a function of Q. So that's good because we can now use Hamilton's equations to work out what the equations of motion are. Okay, so the equations of motion are going to follow from Hamilton's equations. So we know that x dot, Hamilton's equations are a pair of first order equations. We've got dh dp will give me x dot, so we can just very easily work out what dh dp is above. So we find that it's p over m, and we can work out what the first order equation satisfied by p is, so it's minus dh, and as I said, in this case our coordinate is given the value x. Okay, so we want to do dh dx and we get minus ax. So in Hamilton's formalism, we end up with two first order equations. Okay, so a first order equation for x dot, or involving x dot, and a first order equation involving p dot. Now, if we want, we can get back to a second order equation. Okay, and we can get back to a second order equation by differentiating this first one, for instance, with respect to time. We do that, we get x double dot is p dot over n, and then we can use the second equation to substitute in for p dot, get minus k over m times x. Okay, so we've recovered the result that we know should be true from Newtonian mechanics. It's the result we also found using the Euler-Lagrange equation. Okay, so this is good. Hamilton's version of classical mechanics is returning to us the correct equations of motion. Okay, so we've done a fairly rapid summary of some of the formalism in classical mechanics. It's the Lagrangian and Hamiltonian formalisms. Let me just summarize the key results that we're going to use going forward. Okay, so first of all, we defined this Lagrangian function, okay, which is our function of the generalized coordinates q and their time derivatives q dot, and in general those depend on time. And we said that very often, and usually as a first guess, you should assume that the Lagrangian takes the form of T minus V. Okay, so usually it's just the kinetic energy minus the potential energy. And then once we have this Lagrangian, we can get the equations of motion from the system for this system from the Euler-Lagrange equations. And the Euler-Lagrange equations are that the partial derivative of L with respect to Q equal to the total time derivative of the partial derivative of L with respect to Q dot. So that's the Lagrangian, and that's how we get the equations of motion. And the second thing we defined was the Hamiltonian function. Okay, so this is a function of Q and of P instead of Q and Q dot. And it can also depend on time. And in general, this can be constructed from P times Q dot minus L. So this is an example of a Legendre transformation, we said, which allows us to start from a Lagrangian and to work out what the Hamiltonian should be. So the other important result that we used was that we had that this conjugate momentum was the Lagrangian with respect to Q dot. Okay, and then the equations of motion followed from Hamilton's equations. Okay, and Hamilton's equations are a set of first order differential equations. So we have that x, well, I guess I should use Q really. So Q dot is dh dp, the partial derivative of the Hamiltonian with respect to P. And P dot, so it's almost exactly symmetric, not quite, there's this minus sign, but that the time derivative of P is dh times dq. Okay, so those are key results that we're going to generalize when we start to consider what happens with classical fields. Okay, so that brings us then to the end of lecture 1. So hopefully this was a relatively straightforward recap of results that you've seen somewhere before, either as an undergraduate with a dedicated course, or at least during the pre-lecture material. So if there's anything that's still unfamiliar to you, you'll have the chance to talk to your tutors about it during the problem class today. And of course, I'm also open to questions. By all means, please contact me. I'll be happy to talk further on any of the issues we've talked about. In the next lecture, we'll go from classical mechanics, describing the motion of particles, to classical fields, so describing how classical fields behave, and we'll see that much of this formalism that we've just introduced will reappear and can also be applied to understand how fields, classical fields, move and interact.